we learn how to use rows move it, and then if we use Arduino, we can send our rows move it output, which is join value, to our Arduino, and the Arduino we can send to our robot. So this is what we want to do, but because of COVID, we cannot do this uh, prototype hardware. So okay, so we continue with dynamic. Okay, dynamic is a set of equation to describe the dynamic of our robot behavior. Okay, the physics of our robot. If we move our robot very fast, what will happen? We will have much more stronger forces. Okay, faster robot arm will have much stronger forces. Like example here, if I move my robot arm from here to here, if I move it slow, I will not have large force. If I move this one very fast, and here I will have very large force. Okay, if I hit a person, that person may die. Okay, so because of that, we try to understand the dynamic of our robot arm. Okay, the second thing, we want to have the dynamic because we want to simulate our robot arm. If we want to make a simulator, we need to have the dynamic of our robot arm. And second thing, we want to build a controller, a dynamic controller for our robot arm, so that we can avoid this kind of accident, injuries to the person. Okay. Sekejap eh. Okay. And then other than that is we can evaluate our robot, and also we can develop a force control for our robot. Okay. So there are a lot of techniques to calculate dynamic model. Most common use is Lagrange and Newton-Euler. Okay. You can also use generalized D'Alembert equation and Apple-Gibbs, but this will not be covered in this class, and also Newton-Euler. Lagrange is the most easiest way to calculate, but while it is easy to calculate, it requires a lot of computation. You need to have very powerful computer to calculate Lagrange in real time. Newton-Euler is hard to build the dynamic equation, but it have you can use a small computer to compute in real time. So Newton-Euler, you don't need to have very powerful computer. Lagrange, you need to have very powerful computer to compute. Okay. However, both Lagrange and Newton have the same performance in terms of accuracy. Okay. If you want to use Lagrange or Newton, both can give you the same result, but Lagrange require more powerful computer. But today we can buy powerful computer with much cheaper price. Therefore, I want to teach you how to use Lagrange. Okay. So today we will learn how to calculate Lagrange. Okay. So these are some more information regarding Newton-Euler. Newton-Euler have forward and backward recursive equation. It gives tremendous reduction of computation time. That's why a lot of people want to use Newton, and it is important for real-time control application. However, the model does not provide sufficient insight for control designed to the recursive computation. Maybe because of the recursive, we change from analog to digital. So there are some part of the data is lost. Like when we change from analog to digital, we have this loss of information, right? So like this is analog data. So if we change to digital, it will become like this. So because of that, we have some loss of data on this part. So this is the disadvantage of Newton-Euler. Lagrange, it is simple to calculate. It is systematic, compact metric, which is good for control. It is not very convenient for computational. It is hard to have real-time dynamic control, okay, because of the very complex mathematics. So it is hard. Okay. So let's go through Lagrange. Okay. Today we will try to compute Lagrange for a simple robot arm. Lagrange is almost the same thing you have learned in physics during your secondary school, sekolah menengah. You have learned about kinetic energy and potential energy. Can you tell me what is kinetic energy? What is potential energy? Okay, so I will pick a person to tell me. Muhammad Imran, can you tell me? Can you give me an example of kinetic energy and potential energy?
Yes, doctor.
Okay.
Okay. Kinetic energy is when a kid slide down on the playground. Right, doctor?
Okay. Okay. Potential.
Uh, Potential. Forgot, doctor. Potential. Okay, potential energy. When people is running. Right, doctor?
Okay. Uh, Kinetic is correct. Kinetic is like a child is apa on a slide. Okay. When the child is on this part here, the child have the highest potential energy. Potential energy is the highest here. Okay. Okay. When the child slide, the kinetic energy will become highest. The potential energy will become lower. Okay. So in this part, the potential energy is lowest. The kinetic energy is highest. Okay. So this part, the kid is very fast. So actually, when the kid is on this part here, the kid have the highest potential energy. So potential energy is determined on how high of your position. Okay. Okay. Okay, dah nampak sikit. So potential energy is mass multiplied by gravity multiplied by height. Kinetic energy is what? Apa, Imran? Half m apa?
Yeah. Okay. When the kid is at the middle of the slide.
The kinetic energy equation. Can you see my slide here?
Yes.
Half m apa? Apa kat sini? Ingat tak?
I don't remember.
Okay. Maybe it's already 4 or 5 years already. Okay.
Yes, that's physics in form 5.
Okay. It's half mv squared. Okay. So this is K, this is P. So just Lagrange, you just need to get K minus P and you will get the Lagrange equation. And to change from Lagrange to force, you want to calculate the force of something. So you need to do this. You need to uh, differentiate Lagrange, this L here, with velocity, and you need to differentiate this over time minus Lagrange differentiate with position with theta. So therefore you can get the force. So this force is the force of your robot arm here, top, the force of your top here required to move your robot arm. So this is top. Okay. So it's not very hard to calculate Lagrange. You just need to find the K, the P, and then you just need to do this. Okay. You need to differentiate with theta dot minus differentiate with theta, and this value need to differentiate over dt over time. Okay. So let's go to one example. This is a very simple example for Lagrange. Let's say this is a 2DOF robot arm. Okay. So now I want to get the position, the coordinate of x1 and y1, the coordinate here, which is x1 and y1. So y1 is this one and x1 is here. So to get this, it's very simple. We can use the trigonometry, which this part is opposite. Sine theta so equals to y1 divided by L1. So y1 is equals to L1 sine theta. Okay, so here. And for here, we can get by using cos, which is cos theta. So this is theta, which is the adjacent, which is here, divided by hypotenuse. So adjacent is x1 divided by hypotenuse L1. So x1 is equals to L1 cos theta. So now we can have the x1 and y1. Okay. Next, I want to differentiate x1 and y1, differentiate with theta 1. Okay. So what happen if I differentiate x1 d per d theta 1? Okay. So I would like to uh, take 2%. Okay. Siapa nak? Mahmad, can you do this? Can you do x1? Okay. Find x1 d per d theta. And we pick a woman. Okay. Maybe we pick Atira because she has some Al-Quranic verse on her back. She is very pious, orang yang beragama. So Atira will do y1. Okay. So Atira, you will thank me because the next one will be more difficult. Okay. Next one I will pick another 2%, but this one I have picked Atira and Mahmad. Okay, so you guys can also try to solve this one. Okay, okay, Muhammad, what is the answer for to differentiate L1 cos theta? If we differentiate cos theta per d theta, we will get sine, negative sine theta.
Uh, Doctor, yeah. Uh, I will get sine theta over 1 plus uh, sine 2 theta, right?
Actually, uh, you will just get it is correct. You will get negative L1 sine theta.
Over. Over.
So multiply by theta dot. Okay. So that's all. Okay. If you differentiate cos, you will get sine. If you will get negative sine. Okay. How about Atira? So what is the answer this one for
Uh, the
Y1?
answer the answer is L1 cos theta.
L1 cos theta
Cos
1.
theta.
Okay. So that you multiply by theta dot 1. Okay. So yes, correct. Okay. Okay, nice. Okay. Next, we try to find. Okay, thank you very much, Atira. Next, we try to find the x2 and y2. So x2 position is x1 here and here. So x2 is this one. So x2 is x1 plus this one. You will get x2. And y2 is this part here. Okay. We already know how to get y1. So we need to find how to get this value here. So we just plus y1 with this value, we can get y2. Okay. So this is L2 and this is theta. So how can we find the L2? Okay. So this theta, theta 2, and this is theta 1. Okay. So to get this theta here, we need to have theta is equals to theta 2 plus theta 1. So we can get this theta here. So after we get this theta here, we will just do the same thing, which is this value here is equals to uh, L2 sine theta 1 plus theta 2. And this value over here is equals to L2 cos theta 1 plus theta 2. Now we have this value here. We just need to plus with y1. So this is y1, this is x1, and this is y1. And this is this value here, and this is this value here. So we just plus these two, and we will get the answer here. So x2 is equals to L1 cos theta 1 plus this one here, which is L2 cos theta 1 plus theta 2. and y2 is equals to y1, which is L1 sine theta 1 plus this one here, which is equals to this one, L2 sine theta 1 plus theta 2. Okay, now we have this one. I want you to find the derivative for this one. So I want you to find I will do the x2 first for you, and then I will pick 1% for y2. Okay, so maybe that will become much more easier. So what I want to do is I want to differentiate over dt. So I need to differentiate twice. So I need to differentiate d per d theta 1. So because we have 2 theta, so we need to differentiate both. So it is like Jacobian. Okay, so this is L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Okay, and plus and another one is d over d theta 2. The same thing here. We will have, which is L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Okay, let's see here. So this is for theta 1. So if we have theta 1 here. So if we differentiate, we will have L1 negative sine theta 1. Okay. How about this one? We also have theta 1. So minus L2 sine theta 1 plus theta 2. Okay. Okay, next one, we want to differentiate with theta 2. Do we have theta 2 on this part here? This is theta 1. So we don't have, so this will become 0. Do we have theta 2 here? Yes. So this will become negative sine theta 1 plus theta 2. Okay. So now, please try to find y2, and I will pick 1% to help me to solve theta 2, y2. Okay. So who should I pick? Turai Raj, nak try? Do you want to try? Turai Raj? Okay. So I give you 2 minutes. Try to solve y2. So Turai Raj, you just need to differentiate with theta 1 and theta 2 for this one. Oh, let's delete this. Too many things here. Okay. So you just need to differentiate this one. Differentiate with d theta 1. Again, differentiate with d theta 2. Okay, to Raj. Do you get the answer? To Raj?
Doctor, he will use my mic because his mic won't work.
Okay, now I can see the both of you. So this is new. Okay.
For L theta 1 is L1 cos theta 1 plus L2 cos bracket theta 1 plus theta 2, doctor.
Okay, just a second. Raj, you are very fast. Okay, again, L1.
L1 cos theta 1
Okay.
plus L2 cos bracket theta 1 plus theta 2, doctor.
Okay, very good. Next one.
Next one is L2 sine bracket theta 1 plus theta 2.
Why it is sine? So here we have sine. So it should be L2.
Oh, cos,
Cos.
doctor. Cos.
Okay, cos. Okay, perfect. Okay, nice. So Raj, thank you very much. Okay, senang kan? Very easy. So, kacang. So if you have trouble here, you can tell me now. Okay. Do you have any question on this part? Okay. So so if you just follow what we have done here, we will change from position to velocity. Here for the this position here, we change from position to velocity. So this is like kinematic, forward kinematics. This is the Jacobian, if you remember. Okay. Okay, all right. So we solved that one. So now we can jump into our Lagrange. So for Lagrange, if you remember, we need to get the mgh. So h is y. This is h. So this is y2. This is y1. Okay. And another equation is the k, which is half mv squared. So here we already find the v. So we just need to put inside here. This one h is y. We just need to insert the y here. And we can solve our Lagrange equation. So after this, it's very simple. You just need to put all the value inside the kinematic and potential. Okay. Let's go to the kinematic first. So this is for x1 and y1 velocity. And this is for x2 and y2. For the kinematic, for the first joint here is k1, and the kinematic for second joint is k2. Okay. For the kinematic of the first joint, it is half m1 v1 squared. So we know that this is v1 because for the kinematics we need to plus all the energies. So we have the energies that is moving in x direction, and we have the energy that is moving on y direction. That's why we need to plus x1 and y1. So because of that, we have half m1 x1 powered by 2 plus y1 velocity powered by 2. Okay. And you just need to insert here. So you will get the answer will become m1 So this one powered by 2, it will become L1 powered by 2 sine powered by 2 theta 1. And we have this theta dot here, theta dot 1 powered by 2 plus y dot 1 powered by 2. So which is this one, which is L1 powered by 2 cos powered by 2 theta 1 theta dot 1 powered by 2. Okay, so this is the answer for K1. For K2, we will use M2. So the M here, M2 and L2. So it will become half M2 multiplied by V2 powered by 2. So V is x dot 2 powered by 2 plus y dot 2 powered by 2. So we already have the value here. So we just need to power by 2 everything. Okay. So you will get half M2 so this one you need to power by 2, okay? So there's a lot of calculation, but after you fill in all that value here, this one and this one, and you need to power by 2, and you can divide. So anyone that have x1 dot power by 2 and anyone that have x1 dot and y dot theta 2 theta 1 dot and theta 2 dot will go here, and theta 2 dot power by 2 will go here. So you can divide this all this equation into this one, so you will get this equation. Okay, so we will not do this one because it is a bit long, but you can do it on your own. Okay, now we can have the K1 and K2. Okay, so Lagrange, if you remember Lagrange, K minus P. So next is so this one is the kinetic energy. Next is the potential energy. Potential energy is very simple, mgh. So the potential energy at this point here is this one, y1. So the mgy1. So m is the mass, berat. G is the gravity. So y1 is equal to L1 sine theta 1. And for the potential energy at this point here is equals to mgh, which is h is equals to y2. So we just m2g, and this is y2. So we just put y2 value here, and we get L1 minus sine theta 1 plus L2 sine theta bracket theta 1 plus theta 2. So this is the potential energy. Again, L is equal to K minus P. But we have 2K. So L is the sum of K1, Ki minus Pi. And N is equals to number. Okay, I is equals to 1. Which means L is equals to K1 minus P1 plus K2 minus minus P2. Okay. So this is the equation here that I told you. So this equation is equals to K1 minus P1 plus K2 minus P2. So it is the sum of all the kinematic energy and potential energy, and you will get Lagrange. And then for Lagrange, you need to differentiate with theta 1 minus Lagrange differentiate with theta I, and for the theta dot I, you need to differentiate with d over dt. Okay, so this is a very a bit long process. So finally, if you follow this Lagrange process here, you will get this equation. Okay, for this final equation, there are three important things that you can see. This is the term of velocity. This is the term how does the robot move in terms of acceleration. Okay, this part is the term the robot move in terms of velocity, and this is the term the robot move in terms of position. Okay, and the position are affected by gravity. So this term is affected by gravity. This one is not affected by gravity. This one is not affected by gravity. Okay, so this is for this is your robot joint. This is for tau 1, which is for joint 1. This is for tau 2, which is for joint 2. Okay. The most important thing is you can see that the acceleration of the robot, the things that affect the acceleration of the robot is the mass. If you have higher mass, your robot acceleration will need much more power to move. If you remember, F is equal to ma. A is acceleration, A is theta double dot. So this is the force caused by this part, by mass. And then we have the what we call the Coriolis term. This term it is controlled by the robot velocity. And finally, the gravity term, which if we move the robot in terms of position, then we will have the effect of gravity. If we move the robot very fast, we don't have that effect of gravity so much. But if we move our robot really fast, we will generate very high force here.